Our first speaker of this session is Takatoshi Hama from Nihon University, and he's going to tell us about hyperbolicity and exponential growth rate of affine cactus groups of degree 3. So whenever you're ready.
Thanks for the introduction, and thank you to the organizers for giving me the opportunity to present my research today. I'm Takatoshi Hama. I'm a first-year PhD student at Nihon University Graduate School. Please excuse my background. I just moved 2 days ago, and I'm joining you today from my bed. All right, let's get started. In this talk, I will preface the affine cactus group and show the affine cactus group of degree 3 is a hyperbolic group, and give the explicit growth function with respect to the standard generators. First, I recall the definition of the cactus group. The cactus group is introduced by Henrik and Kamnitzer as an analog of the braid group. In the sense, the cactus group is the limit of a braid group. This is the definition. For an integer n, which is 2 or more, the cactus group of degree n is defined by the following presentation. Generators are SPQ, where PQ are between 1 and n, and P is less than Q. These generators have diagrams as like the braid group. I will show the diagrams in next page. These are the relations. Multiplying the same generator results in its identity element. When the index intervals are disjoint, the corresponding generators commute. If one interval contains the other, the generators are swapped through this calculation. The third relation looks complicated, but it can be easily understood using diagrams of the generators, just like with the braid group. These are the diagrams. In the case of degree 4, stacking the diagrams corresponds to multiplication. The difference between these diagrams and those of the braid group is that the crossing points can have 3 or more strands. The top diagrams are generators 1. For example, S14 has a diagram like twisting 1, 2, 3, 4, 2, 4, 3, 2, 1. Yeah. S12 twists 1, 2, 3, 4 to 2, 1, 3, 4. S34 twists 1, 2, 3, 4 to 1, 2, 4, 3, and S24 twists 1, 2, 3, 4 to 1, 4, 3, 2. The bottom diagrams are means the relations multiplying the same generators result in its identity. If the intervals are disjoint, they commute. And the third one is this. The larger intervals are swapped as they are, and the smaller ones are swapped by moving to a position symmetrical to the center axis of the larger one. These are not relevant to the main topic, but it helps to understand the definition of the affine cactus group. This is the definition. For an integer n, which is 2 or more, the affine cactus group AGN of degree n is defined by following presentation. Generators are sigma PQ, where PQ are between 1 and n, P and P is not equal to Q. Relations look even more complicated than cactus group 1, but we can also see them simple by diagram of generators. Let's look at the diagrams. First, we draw the strands on the cylinder and we number them. Once you cut it open, you can understand relationship just like before. Now most of the preparations are complete. Here are the main result. Theorem 1. The affine cactus group of degree 3 is a hyperbolic group. Theorem 2. The growth function of AJ3 with respect to the standard generating set S is equal to this. As a corollary of Theorem 2, the exponential growth rate of AJ3 with respect to S is equal to 2 plus square 3. Before we get to the proof, let's first address the word problem. By moving the longer intervals upwards, we can obtain the canonical form of the elements in AJN. Thus, the word problem is solvable. For a more detailed explanation, please refer to Genevois result. Then, here is sketch of proof of Theorem 1. First, recall this well-known fact as a lemma. Let G be a group. Then, if G acts Hn, it's hyperbolic plane or more higher dimension, and properly discontinuous, and if G acts properly discontinuous and co-compactly, then G is a hyperbolic group. So it's sufficient to show that AJ3 acts hyperbolic plane. To find it, let's draw the Cayley graph. This is the Cayley graph with respect to the standard generators. The 6 relations give 6 cycles around each vertices. For example, sigma 1, 2, sigma 1, 3, and equal sigma 1, 3, sigma 2, 3, spans 1, 2, 1, 3, 1, 2, 1, 3, 2, this cycle. And just grew 2 cells for each cycles. We obtain the Cayley complex CAG3S, and CAG3S is isometric to the hyperbolic plane H2 up to scaling by corresponding 2 cells to the squares, and it's give the tiling of H2. Therefore, AJ3 acts on H2, and we obtain that AJ3 is a hyperbolic group. And next, I will present a sketch of the proof of Theorem 2. First, let's consider the sequence AN. AN defined the number of the vertices. It satisfies the word length with respect to S is equal to n. And next, set up the recurrence relation. Let the vertices represented by white circles have a word length of n. Vertices with a word length of n plus 1 are of two types. Those adjacent to two white circle vertices, the white triangles. And those adjacent to one white circle vertices, the black triangles. The number of white triangles is equal to the number of white circles. And so we can count the vertices with word length n plus 2, white square and black square in this way. 4 times an plus 1 minus an plus 1 minus an, and white squares is can be counted by 3 times an. 3 times an. Then we obtain the recurrence formula. An plus 2 equal to 4an plus 1 minus an. Therefore, by solving it, an is equal to this, and the growth function of AJ3 with standard generators is given by this, and just calculate it, we obtain this result. For corollary, just calculate this. It's equal to 2 plus square 3. Although the results this time were simple, but I believe they will be useful in discussions about higher degree. That's it. Thank you for your attention.
Thank you very much. So maybe let's thank the speaker first. So is there any question from the audience?
Yeah, so what about 4 and above?
Now, about 4, it may be hyperbolic, but maybe. But I have not drawn the K graph, so maybe that's me.
Yeah,
Just
maybe
correct.
the hands-on technique that you have for 3 is going to be difficult to continue. Yeah.
Maybe gonna be difficult, but I'll try.
I guess you could put the presentation into Gap or something and ask whether it's automatic or all those sort of things. But I guess it's too big.
Yeah, maybe too big.
Yeah.
I have tried for the cactus group by using Gap, but it's too big.
Yeah.
It was too big here.
Okay.
Thank you for your question.
So it looks from your proof that you actually show, from your proof of hyperbolicity, that you actually show it's cubulated. Is that right?
Please pronounce more slowly. I can't.
Yes. So it looks from your proof of that AJ3 is hyperbolic, that it is also cubulated. Is that right?
Yeah, that's right. I use the
okay.
cubulity. Yeah. The K graph of affine cactus group is cube complex. So I use it.
With hyperbolic. So it's cat minus 1, I guess, because it's got hyperbolic.
Cat minus 1.
And also you've computed the growth rate for the standard generating set. Do you have any other idea? Do you have any idea about if you change the generating set, do you get a different growth rate? Do you know if what you found is like the optimal growth rate?
Fine.
So you've computed the growth rates for the standard generating set. But maybe if you change the generating set, you get a different growth rate. Maybe you get a smaller one. Do you know if the one you found is minimal? Do you have any idea how you could compute the growth rate for other generating sets?
It depends on, yes, of course, that depends on the generating set, but I have tried to calculate about just about standard generators. So minimal generations may be more smaller and more bigger.
Yeah.
But I don't know. I try it.